nothing to do with the sponsorship. I just showed up today. So who here has heard that interpretability is something that we should care about? Excellent. I'm not surprised. Like many other words, bias, fairness, we are intrinsically, most days hear those words in conversations that this is something that we should move towards. I think that my talk today is very much a discussion where I'm hoping to push you on what do we actually mean when we say move towards more interpretable machine learning. And what do we actually, what is the finish line? And how does this vary depending on the problem? A little bit about me beforehand is that I am a researcher at Google Brain. My area of research is how do we explain the model predictions of deep neural networks. I also started a nonprofit 4 years ago called Delta Analytics, which does a lot of pro bono volunteering for nonprofits all over the world. And we have engineers and data science come join. My parents are self-described hippies, and I grew up in many places around Africa. They met in Sudan. I grew up in Mozambique, South Africa, Swaziland, Lesotho. They just moved to Liberia. But currently, I'm residing in Mountain View. Today, I'm hoping to cover a lot. I got excited. I tend to add more slides as I'm thinking about new concepts. So I'll calibrate as I go, but please feel free to throw out questions along the way. Because I think a lot about this discourse is just talking about and grappling with the ambiguity of moral terms and how we apply them to technical fields. And really, the first question that I want to ask is, why are we compelled to go beyond accuracy? What is our motivation? And to frame this question, it's useful to think that just 50 years ago, we were just obsessed with accuracy. And mainly because when we started thinking about fields like computer vision in the 1940s, we were trying to create machines that would see the world like people. And this was extremely difficult for two reasons. Because humans are very good at seeing the world. And secondly, because it's a very high-dimensional problem. And so there's many different types of computer vision tasks. I'm going to talk about classification today, where we try to identify a single object in an image. And when we started this journey in the 1940s, much of the research for the next 50 years was handcrafted features. It was trying to reduce the dimensionality using features that humans thought were necessary for vision. So it was things like just using pixel histograms that would chart the number of pixels in an image, and that would be able to uniquely identify what the image was. These features were easy to interpret because the humans defined the features. But we didn't make that much progress. Some are very good for specific tasks. Like this is a fantastic example of features that were specifically for identifying human faces. But as soon as we try and apply that to identifying a snake, not so great. And they also tend to involve multiple steps. So often your pipeline looks like you're doing this feature, you're adding another feature, you're tweaking, you're reshuffling. Enter CNNs, convolutional neural networks. The power of CNNs was that it was a single differentiable function, and the extraction of the features was delegated to the model itself. And so instead of telling the model what features to extract, we're allowing the model to select these features according to the feedback that we give it about what is right or wrong. In 2012, a team called Supervision from the University of Toronto, led by Geoffrey Hinton, just slammed the competition, so on the ImageNet competition. And so ImageNet is this annual competition which is run where different research groups attempt to increase the accuracy on classifying 1.8 million images. And so before that, the second closest competitor in that year, actually, I think I wrote it down. Run-up was at 26.2% error, and it fell to 16.4%. So pretty much after that, every year, everyone has focused on CNNs because it was seen that all the other approaches were not comparable. So before CNNs, we had these hand-engineered features. We had mediocre performance, very good for very narrow tasks, but pretty much off the cliff as soon as we try and include many different classes. But it was generally considered to be very interpretable. And the features were easy to understand because they were defined by humans. And then CNNs, we've achieved this superstar accuracy compared to what we were doing before. But we now have this problem where we have this kind of undesirable descriptor that we attach to CNNs where it's a black box model. It's seen as very opaque. It's seen as not clear how to understand how it arrives at a given prediction. And in some cases, especially on tasks where the model is better than human performance, it's unclear how we weigh. How do we treat such a model in society if a human cannot be the checker? Where does that leave us? It left society kind of grappling with a new problem. The same way that all of you raised your hands at the beginning of this talk, there's just been an intense amount of discussion and debate about how do we use models that are perceived to be black boxes in domains that have an impact over many people's lives. And this is where it becomes clear that in certain contexts, accuracy is not enough. This is really where this talk starts. Because despite the gains that convolutional neural networks have given us, there seems to be a consensus that models should be interpretable. I'm curious how many of you agree in this room with that consensus? Oh, excellent. OK, cool. Yeah, I like the support for my subfield of research. I think one of the questions I want to push you on today is that there's many nuances to any statement of what we desire about a given tool. And machine learning, like any other, is a type of tool. And I'll talk through some of the challenges that we grapple with a lot as researchers in the subfield of interpretability for machine learning. But firstly, I'll kind of introduce some of the motivating reasons that are commonly given for why we want interpretability as well as accuracy. The first one is that there's certain tasks that are so sensitive that if there's an incorrect action by a model, it will have an intolerable effect on human welfare. These are tasks where already even humans acting as the decision maker face an enormous amount of pressure to get the decision right. These are things like self-driving cars, medicine, credit scoring. And here we need to be able to explain how a model arrives at a decision in order to prevent calamitous harm. The second reason that is commonly given, actually, this is a very interesting kind of reflection point. The fact that we think that there's some tasks that demand interpretability suggests that there's some tasks where we may not need it to be interpretable. And I asked earlier, like, who thinks that we should always have this property? In fact, I believe that we don't need all models to be interpretable. And I'll give you some insight into that. It's mainly because there's varying degrees of impact that a model has. And in fact, there's many models where even if it's not interpretable, we can still use it and get value out of it. And it's OK to accept this. And these instances are things like this. The cost of an incorrect model decision is very low. Let's say you get a bad recommendation one day. You get suggested a product that you had already bought. That's a terrible, incorrect decision. It's not desirable behavior. It might make you frustrated with the company, but it's not going to alter your human welfare in a significant way. There's sufficient empirical evidence of consistent behavior. This is a very interesting one, because over time, if we observe consistent behavior after deployment of a model, we may feel there's sufficient trust that we've observed the model under various different data samples outside of the training sample, and we understand how it behaves. We understand where it does well and where it does badly, without needing for it to be fully interpretable. And then this is a very important one. So about 2 weeks ago, I got a comment on a blog post I had written, and it was a very passionate comment. It was saying, we should just enforce that everyone release the weights of their models. And that by releasing the weights of the models in the public domain, we can really nail this interpretability thing. And yes, I think that releasing weights of models for someone who had the technical ability to leverage those weights would provide some degree of interpretability over the status quo. But it also opens up vulnerabilities such as privacy concerns or security. And so we need to weigh how we gauge interpretability amongst other concerns, like what we reveal about a model that can be used for undesirable purposes. The second two reasons that are often stated actually make a lot of sense. So proactive and retroactive. So I'm an engineer, and I take my responsibility seriously. And if I can make my model better before I deploy it by gaining insight into what it's bad at and where there's data inadequacies, then I want to. And I think this is very sincere on part of many people in this community. In fact, part of the reason you're probably at this talk today is because you sincerely feel that you also have a responsibility to make sure that the technology you deploy meets some of these criteria. There's also the retroactive. So when a model makes a mistake that has an impact on human welfare, we're accountable. So we should be able to explain what went wrong. There's examples like this, like self-driving cars comes to mind, where it's the loss of human life. And in that case, we need to be able to say, why did our model behave in such a way? And how can we prevent it from happening again? The fourth reason is because we're scientists, because we want to know more about what's happening with deep neural networks. A lot of the most fascinating papers that have come out about interpretability are not about a specific model. They're not about a specific task. They're really papers about how insights given a set of models tell us a lot about deep neural networks in general, how they train, why they work, what can we do to generalize better. So I told you all this, but I actually haven't told you the main ingredient that we need to measure progress on this task, which is that we have all these great reasons that motivate us to care about interpretability. And that's why we all are spending our time here this afternoon. But how do we know when we reach the finish line? I'm curious if there's people who have a thought on this that want to. Courage, courage. Yes, in the back. Excellent. Oh, interesting. That's actually, so what that is capturing, and I'll just repeat it. So what the gentleman said in the back, he said, when a model is able to convince a doctor to go against his own decision. So that captures an interesting phenomenon where a doctor, a human expert in this domain, is willing to trust the model over their own judgment. I think that's quite insightful, because that's capturing both the fact that even in cases when we differ from a model, we still think they may have made the better judgment. Yeah, what else? Go ahead.
It could be that the model provides evidence in the form of things humans understand intuitively as opposed to things that require additional analysis. So your first example, human-coded features, if a model produces something like that, you look at it and say, oh, let's take another chart that goes. Whereas now, you give me a call with a billion weights, math is required.
Oh, interesting. So what's being described there, and I'll just briefly repeat it, is this idea that there may be various levels of interpretation. You may have the weights, which was the suggestion. Just dump the weights, put them out there. But you may also just have a correct interpretable, well, I hesitate to use interpretable here, but you may just have an image with the correct label, and it seems to make sense for a human. So there's varying degrees. I don't know if that answers the question, but that hits on an important point, which we're going to touch on. One more at the very, very back.
Several experts explain the result or the finish line, and they offer similar explanations.
Ah, I see. So you're saying, do you mean, and in this case, do you mean an ensemble of models, or do you mean a set of human experts? I see, I see. Actually, that's a very common approach currently to interpretability. There's a group of doctors, you ask them what do they all think, and then you compare it with your model. So that's interesting. We'll get to that. I'm going to move on just so we keep things moving, but then feel free. Are we there yet? So this really boils down to when do we know we've made it? When are we happy? So it's tricky. I think this is a human concept. This is a value-laden concept. And this means that we're unlikely to arrive at a clean finish point of what constitutes an interpretable model. It's likely to actually evolve with our view of the technology and our understanding of what we expect. And this is the key takeaway, number 2, is that interpretability does not actually require explaining everything about a model. It doesn't, an interpretable model does not necessarily mean the weights of the model. And this is because the level of interpretability that would satisfy different people actually depends upon their vantage point and their downstream task. So I'll take an example. I flew in last night, and you often hear when you're on a plane, you often hear, oh, there's a technical trouble, they're redoing some additional safety checks. So that chain of communication is actually, you're the last one in the chain. And probably the first one is the ground crew, who spot something incorrect with the readings from a sensor. And the way that they communicate amongst themselves is actually probably very precise, because they need to identify which sensor, they need to call other people to look at it. The intermediate person who has to be alerted is the pilot. And there, it's much more relevant, like how this affects him, like what he should be paying attention to. And then I'm actually the last cog in the chain. I'm just, you know, in the cheap seats, and they're just telling me I'm delayed another hour. And so, in fact, like this is not an incorrect approach. This is a sufficient amount of information for me to do my role, which is just sit there. And it's very much the same for interpretability. It's unclear that giving everyone the weights to the network is particularly useful or is what people need, because there are multiple different agents in any situation. I'm a researcher. I'm also a consumer. I'm also, I would say, I'm also very interested in how communities as a whole deal with this issue. And everyone is different. Another thought is that, like, as a society as a whole, we also have an evolving perspective towards interpretability. Just the same way that the research community 50 years ago was obsessed with accuracy, now we're very acutely aware of interpretability. And that may evolve or change over the next few years as we become accustomed to certain technology, as we gain empirical evidence for how models perform, and as legislation takes place. Because often our views of certain words are very anchored actually to the perspective of the legislators. For example, if I ask an American what freedom means to them, whether they agree with it or not, they're likely to reference the Constitution at some point. And so there's all these fascinating concepts that we have as a society when we think about desirable properties. And the real interesting question is, how does that mesh with technology that we deploy into the world? And given that interpretability is a human-centric concept, we are often most concerned with what differs from how we do a task. This was mentioned several times. How does this differ from the crowd of experts? Does the doctor defer judgment? And this might be, does it align with how a human approaches a task, or does it differ? And I think this is one of the other misconceptions, is that we often think that the above is right, that it aligns, and the bottom is incorrect. And it can be more nuanced than that. The desire for interpretability is not only motivated by failure points. We're not out here, we're a lovely bunch of researchers. We don't want to just punish people. Like I think there's also just a natural human curiosity of what we can learn about approaching new tasks. So this was so much fun. I actually went to the OpenAI Dota versus OpenAI challenge. It was like 2 weeks ago. So for those of you who don't have context, Dota is a game. It's a very complex, rich game. And OpenAI was launching their AI set of bots against a human team. So they just trashed the human team. It was like, they had like 4 matches, won 3 of them, and then the 4th was like severely handicapped. And so actually like the whole exercise was frankly one of interpretability. We knew that they were really good. We knew that after like half of the first game. Then everyone was really excited about how were they doing this? Like why is it possible? What is different about their gameplay than human gameplay? And in fact, this is the same thing that's observed with AlphaGo players, with Go players. So like after AlphaGo beat had several successful rounds against human players, there's now a lot of YouTube videos from enthusiasts who are interested in like, what can I learn from this algorithm? And what are these unusual patterns that I can't see that the model can see? But I think it's time to ground this a little and think about how do we actually do this right now? Like what do we actually do to interpret deep neural networks? And there's 2 possible approaches here. So one is that we build a new model that's interpretable as our starting point. The second is that we interpret a model that's already built. We have a trained model, and then we go from there. Can we interpret what it has learned? This is actually being the subject of very little research. Starting out wanting to do an interpretable model. It's very different if you like handicap yourself and you choose like a model that's thought to be inherently more interpretable, like a linear model. But actually, I'm talking about the latter, which is like you try and create a complex model which is also interpretable. And so it's a very rich area of research. In fact, most of research is overwhelmingly focused on interpreting trained model. And that's already quite a constrained space. Because in fact, like you're already, your degrees of freedom are limited because you're starting from the vantage point of something which has already been trained only to optimize your loss function, which has nothing to do with our concepts of interpretability. The other thing I'll say about this is that we've overwhelmingly focused on computer vision models. Today, all I've talked about is computer vision. Very little research has touched upon audio or language models. And so this is an incredibly underserved area of research. But given that, what are the common approaches now? One is model distillation, where you essentially try and teach a student model the essence of the parent model while maintaining accuracy. And the student model, the criteria is it has a simpler, perceived to be more interpretable functional form. The second is that you try and interpret components of the model. So you say, what does this part of the model do? How will, like, is it important? Is it not? And then I guess methods that estimate importance of a given input. There you're trying to understand, what does this pixel do? Is it important to the end prediction? And finally, you have tools which require that we determine that we set the question at the outset. So to make this concrete, model distillation I talked about. So with interpreting role of importance of building blocks, that tends to be weights and filters. Is this, you may hear at some point, is this the kitty filter? Does this detect kittens? It's tricky. I think it's very nuanced whether we actually know what these neurons are interpreting, but it has been the subject of a lot of research. And then there's models which interpret the importance of an input. So what you see an ostrich, and then you also see a heat map which represents the importance of a pixel. So lighter pixels, that's actually a ranking. Lighter pixels will be estimated to be more important to the final prediction of that being an ostrich. And then finally, these human-guided tends to be things like this TCAF, which essentially requires that the user contribute photos and sees concept vectors. And then I'm sure a few people are familiar with TSNE. So we have a bunch of methods, right? And we have some sense of what we want to do. How do we choose the method that's right for what we want to do? How do we evaluate the goodness of an interpretability method? Question. Oh, excellent. Oh, excellent. I like your thought process. You're saying, let's take the interpretation, let's put it in a loss function. I don't quite see how the structure doesn't immediately come to mind, but you're saying let's explicitly see if it works as an optimization piece. So the part about like us thinking more about if we can explicitly optimize for interpretability, I really like. A lot of these methods that I mentioned, I don't instinctively know how I would reformulate that as a constraint in the loss function, but very good thought. Yeah, who else? Ah, interesting. Yes, yes. So actually, there's very interesting work in model compression, which I also find fascinating, which could be a good subject for this, because there's two desirable properties there. Smaller models are also better for mobile first AI, lower latency, lower memory, and so yeah, I would say go for it.
We can say a model is interpretable if we give it novel inputs and we correctly predict what the output will be. If we give it tons of animals,
yeah.
an animal it's never seen before, and we say, this is going to break this model, and it does, or this is going to be funny. It's a dog, but it's going to think it's a cat, and it comes out.
Yeah. So you are absolutely hitting the nail on the head. So that's a key way that researchers test some of these methods is they do human studies. The researchers actually interact with other humans doing this. But they ask whether, for example, does this make sense for them doing the same task, which is precisely what you said. They also do other things. What else do you think we should do? Ah, excellent. Yeah, so we term that ablation studies. So that's actually an interpretability method in itself, where we say we will remove the part that you consider. Actually, to be fair, it could also be an evaluation method. You remove the part that's estimated to be most important, and you see if it's in fact important. Yeah, very excellent point. I'll take one more, and then. Oh, so sorry. Yeah, go ahead. Go ahead. Yeah, I think what you're hitting on is actually an excellent. So the question that I asked was the same as the earlier one, but the response here was actually very similar to your response, which is that essentially we want to think about what is the correlation between some characteristics of the model and interpretability, and maybe like optimize for that directly. I actually think it's very hard to evaluate what makes a good interpretability method. Mainly because, let's say we even look at this, which is ranking the inputs. There's many different methods to do so. They all have different outputs. And we're left with now what? Like, how do we determine what the best one is? Let's say we're not prepared to go and do a new interpretability method. Let's say we just want to pick out the existing interpretability methods proposed. And we have no ground truth. And so I think a large subject of my research is we should define desirable properties that we think are important. And we should formally evaluate these properties. And another key theme in my research is that we must understand that interpretability method must not only be meaningful, but it must be reliable. And it must be reliable first, because if it's not reliable, then why are we using it at all? If it's not an accurate reflection of the model, then how can we even take anything that it place any weight on what it says? And so the gentleman here talked about human studies. This is in fact a big component. A lot of my research has been saying we also need reliability benchmarks. That it's not enough for a human to trust it. We also need to make sure it's an accurate reflection of the model. And this is a very interesting subject because there's many unexpected points of failure with existing methods where they fail to be an accurate reflection of what the model places importance on. This is work that I did with colleagues last year where it was possible to essentially manipulate an explanation by just adding a simple transformation to the input. It doesn't affect the model, but you're able to disrupt the explanation to look like a kitty cat and patchwork. This is a work done by one of my colleagues where they show that even if you randomize the network completely, you have explanations that don't change. And this is problematic because you want your explanations to change when the network changes. You want it to be an accurate reflection. And then this is work that I just completed with colleagues where we say, hey, and it was very similar to what a gentleman there said. We said, hey, if a natural logical starting point to this conversation is these estimates should be able to identify what's important. So then we ask, well, OK, let's remove what they said is most important, and let's actually rescore using the model. Let's retrain. And if it's actually very important, it will damage the model a lot. And if it's not important, then you won't see as big a drop. And our big comparison was, what if we did this randomly? Essentially, why don't we compare each of these methods to a random guess as to what is important? And so our results were very surprising. We showed that all the estimators that we did benchmark were worse than a random guess. But there are certain transformations that really do improve the accuracy of these interpretability methods, which make them much better estimates of what is important to the final contribution. And this is part of a larger philosophy that I think is very interesting as a roadmap, which is that we need to be more articulate about what we mean by desirable properties. And then we need to create formal treatments where we evaluate these properties. And at least by doing that, we have some way to measure progress and have a discourse about what we want. So I shared kind of two of my thoughts on the subject today. One is that it's an elastic concept. Interpretability will vary depending on who we are, where we are, what we need to do. And that makes it very difficult to implement technically. It means that we should understand there's many desirable properties and that articulating those properties is the most important first step. And the second is that we are very tempted as humans to create simple stories that are attractive. And I unfortunately think research has fallen victim to this as well. A lot of the tests that I described earlier are actually very simple implementations of just the scientific method. You start with a basic hypothesis. You're evaluating these methods compared to that hypothesis. And yet we found that many methods failed to satisfy the requirements. And so we need to become much more precise about what we require. It may be a more attractive explanation. It may be more intuitive. But if it's fundamentally an incorrect representation of the model, we're back to square one. Oh, excellent. Let's chat. I don't know how much time I have. I sense I'm bordering on none. But I know that, sorry, you had a question earlier. Or you were going to contribute earlier. I would love to still have your thought on the subject. Oh, I guess just I can repeat if you.
Yeah, I'm trying to speak. I can put the mic out. Actually, it's going to be break time next, so no one's coming right in here.
OK, cool. Yeah. Also, please disperse if boring, or if but go ahead. I guess I can shout out the first one.
I was going to say I've had some experience with interpretations, like so. There's Monrovia and Westerns.
Oh, Lime. Yeah. Excellent.
It's available both in Python and R.
Yep.
And that way, you take each classification. So if you run the Lesotho model, you find which those features you perturb them. You find out which ones.
Yes.
And it's done in a way that humans can understand well.
Yep.
Another one is Shapley.
Yeah, Shapley. Oh wow, we have excellent. You should do the encore round up here.
And then there's a third that's kind of from a much different angle. This one is specifically for convolutional neural networks, which actually work very well.
Guided backprop.
It's called Net Dissect.
Oh, I see. It's by Bole Zhu, I believe.
Yeah, I think that's
OK, excellent.
author. And what it does
Yeah.
So you can attack it from, like in the Rivera's paper, they showed that they applied the Usenet for attacking
Yep.
and remove an email, like somebody's email address. And then in another one, they used the wolf husky.
Yeah.
Fragment the image into.
So what's being described here is there's more interpretability methods, in fact. So Lime is particularly, I think, widely used, and it involves imposing a linear model on top of some of the high-dimensional space. There's recent work which does show that it has some failure, perhaps. I'll dig up that paper, but I think what you're describing is, in fact, like even more ways that we can think about this problem.
I just see that people are able to apply that
Yeah. Yeah. And I'll say one more thing on that, is that those are also researchers who have made the effort to open source their code in sustainable ways, which is very problematic for research as a whole. And I think it's something that we're grappling with as an issue. There's just not the same culture that you find in other parts of engineering with code release. And so one reason why these methods are so popular is because these authors have actually taken it upon themselves to present a good code base. Sorry, here.
So partly following up on that, it feels like some of the model interpretability concerns, maybe there are more problems of will than ability.
How so?
If there is actually good tooling, and I care to follow up about model interpretability, I may be able to do so. When it's impossible. But a follow-up on that, I actually, like my concern with model interpretability is sometimes the ethical implications of my success. So it's not, I want to understand why I failed in the failure modes, but like even a recommendation system can be selling and the chestnut of airline tickets to Vegas for people who are schizophrenic. Like, there are ethical implications to my accuracy that I don't necessarily understand in what feel like relatively benign domains.
Yep.
And I don't have any desire to pursue interpretability when I'm already successful. But there's a lot of ethical concerns hidden in that success.
So, excellent. There's like two questions there. One is, do these methods pass the check? Should we just go ahead with the methods that the gentleman stated? No, I think so here's a few questions I didn't ask in my presentation. And it's not no, because I actually really respect the work of these authors. And I think, in fact, like part of the conundrum is that this is such a tricky task to make progress in. But I'll ask you one question. Oh, I lost the projector. But essentially, like those methods, a lot of what you described, they give a heat map for a single image. Let me ask a question to the room. At what point do you feel that you would feel comfortable checking off on a model after seeing an explanation for a single image? How many, would you have to see multiple images? How do you use that information, that heat map? What do you look at? How many heat maps would you look at before you say, okay, good to deploy? 27%? That was like such an exact number. That feels like a real life story. I looked at 27%. Go ahead.
You have to see a number of failure rates because it doesn't.
But how?
You see a leopard and then see.
Yeah. But how do you define failure rate? That's another secondary question that's present here. Is that, say that I have a heat map. We saw a heat map for, what animal did we see a heat map for? Ostrich, yeah. I couldn't remember what I threw in there. Yeah, we saw a heat map for an ostrich. Let's say the most highly ranked pixels weren't directly on top of the ostrich. Let's say they're like, the tail's highlighted, but then the back is highlighted, the background a little. Is that a fail?
Are you looking for a Boolean response from the model? Ostrich, not ostrich, or are you looking for...
So the correct label is ostrich, and we're just trying to understand what the model pays attention to. But if it's not directly centered on top of the ostrich, would we call it a fail? I guess all I'm suggesting here is that, in fact, even how we determine whether this explanation is correct or incorrect, there's ambiguity there. And then we're looking at a single example. So the question remains like, how do I know I just was unlucky? ImageNet is 1.8 million images. Do I go through all those images before I'm confident to release? Go ahead.
Yeah, it seems like you're never going to have confidence as long as it's just looking at two-dimensional images and doing the standard Recepton convolutional method. It's going to have to say, okay, that's an object about a meter across, roughly spherical,
Yeah, interesting. You're speaking to another concern of interpretability, which is that often the concern about deep neural networks, which I think is a very valid concern, is that it's not conceptual based. Like humans have very good understanding of concepts. We understand what a classroom is. Fundamentally, we know, that it involves chairs, it involves learning, but it's not clear a deep learning model actually knows anything about what a classroom is. It just learns to identify if there's a green board on the wall, the probability is higher it's a classroom. And so I think that's not necessarily, I guess, saying how we should use it, but it's bringing up another reason why we need to have more interpretability, because those are considered often failure points. And so how do we understand when it's doing that to a large degree? Yeah, you would want to know a method who would tell you that. And I think that, in fact, what you're describing is actually one of the most problematic reasons we really do urgently care about interpretability. Because maybe I'll just briefly, it might be of interest to some people, but there's even a case, there's often correlations in our data set which we'll never see in the real world, which is in fact that we often see in these pictures pandas on ice. And so what's learned is this correlation between pandas and ice, and that's the only time it's classified correctly. But in fact, like as humans, we know even if we see a panda in a zoo and it's not on ice, we still know it's a panda. And so there's this fundamental, like as you described, well, how do we impart conceptual understandings of how things relate? Maybe, yeah, go ahead, sorry, in the back. Sorry, what was that term? Out of their gluts? Excellent. Yeah. Yeah, I sense we're reaching, well, I hesitate to make big prognosis, but I do think what you're stating is correct. We've really focused a lot on the architecture. I mean, basically 2012 to present has been architecture, architecture, architecture. We take data as given, we do minimal pre-processing, and then we take the task as given. We use the same 3 data sets, MNIST, CIFAR, ImageNet, and then it's all about how do we optimize essentially this mapping. But in fact, there's a lot of degrees of freedom in both the data set. I mean, how is it presented to the model? Is there interesting things that we can do there? And I also say the one that never really gets talked about is the hardware. I mean, think about it. Why is deep learning possible? These ideas have been around for a while. It's really a combination of hardware and data that allowed it to take premise. And what can we do to make hardware that's even better tailored to different models and like different ways of mapping? Because a lot of what makes us successful is the tools that we're given. So things like the Google initiative to design a TPU specifically for deep learning, I mean, that's very promising, because I think that's actually your biggest constraint is what can you run on? Because that, in fact, defines the cost of operations. In some cases, it oddly seems to affect accuracy, which it shouldn't. So there's all these nuances to how we implement our code. But I completely agree with you. Yeah, sorry. Yes.
And oftentimes, the accuracy is dependent on the narrative. So when we're releasing results, we need to be clear and precise about what our context is, because narrative shifts and
So maybe just to clarify, are you saying that the results that we release don't translate into the real world, or are you saying that like we should?
I'm saying that you can have multiple results that are accurate, but are essentially opposing because the context.
Oh yes, absolutely. Yeah, I mean, essentially, that's another big shortcoming I would say we as a field need to get better at. We're all using these 3 data sets to publish all these results. What happens as soon as someone who's actually working in industry tries to take one of our approaches? You're going to work with real data, and real data is messy, and most of the time you're trying to understand how does my model actually grapple with a different deployment distribution than the test. I mean, really, this is where we're removed, and because of that, we're not tackling our constraint is not driving a lot of very innovative approaches. But yeah, I totally agree. I think
So
we're out.
Sara,
Yeah.
this
Thank
was
you.
fantastic. Let's all give her a round of
Yeah,
applause.
thank
This was great.